In this video, we will solve a problem that was asked by a brother on Telegram channel of Economaths. The question is like this. Consider a closed economy in which an individual's labor supply to firms is determined by the amount which maximizes her utility function. So, labor is being supplied by an individual to firms according to the individual's utility function, that is UCL is equal to C to the power alpha 1 minus L raised power beta. Alpha beta are greater than 0 and alpha plus beta less than 1, and C is the consumption expenditure which is taken to be equal to the wage income, that is WL. Then we are being given these very options. We need to find out which option is correct. First option is labor supply does not depend upon the wage rate W. Second option is labor supply is directly proportional to wage rate W. Third option is labor supply is inversely proportional to wage rate. And last option is more information is needed to derive labor supply. Okay, so the stuff we want to find out is the labor supply. We need to find out the labor supply and see whether it depends upon the wage rate or not. Okay, so what we are being given here, we are being told this is the utility function of the individual, that is UCL. Okay, consumption expenditure and labor is equal to C to the power alpha 1 minus L times beta. Okay, this is the individual's utility function, and we are also being told that consumption expenditure is equal to wage rate. Okay, so we are also being told that consumption, that is C, is equal to WL. Okay, what will we do here? We just plug this C is equal to WL in this utility function, so our utility function will look like this. So in place of C we have WL and L is equal to C to the power alpha, that means WL raised power alpha 1 minus L raised power beta. Okay, so this is the utility function of the individual in terms of consumption expenditure also. Okay, we want to maximize the utility function of the individual. Okay, how do we maximize the utility function of an individual? Okay, if we are being given any utility function, okay, we are being given any utility function, if we want to maximize the utility, what we do, we just take the derivative of utility function with respect to some the parameter which is here L, and we set it equal to 0. That means our utility, let me write it here, total utility will be maximum when marginal utility is 0. Okay, so we have seen number of cases of this. So if this is our total utility function, it will be maximum at a point where marginal utility is 0. Okay, so corresponding to this, when marginal utility is equal to 0, total utility is maximum. Okay, same process we apply here. So the path is something like this. This is our total utility. To find out the marginal utility, we just take the derivative of this function and set it equal to 0. Okay, so our let me write it here, total utility, or simply utility is maximum when marginal utility in terms of labor is equal to 0. Okay, now what is marginal utility of labor? So marginal utility of labor will be equal to the derivative of utility function, okay, which is, so let me denote it by only u. Okay, so to say the space, so when the derivative of utility function with respect to labor is equal to 0, then our total utility will be maximized. Okay, so in this process we will see whether labor supply depends upon wage rate or not. Okay, so taking derivative of this function with respect to L and set it equal to 0. Okay, so which implies now taking derivative of this function here, so we have two functions here. We use the chain rule. How do we apply chain rule? Let's write first this function and then this. Okay, let's write 1 minus L power beta and take derivative of the first function plus we write the first function as it is, which is alpha, and take derivative of second function 1 minus L beta. This is how do we take the derivative. Let us say we have f of x and g of x. Okay, if it is u is equal to this, if we have two functions, what we write derivative of this function with respect to x will be equal to, we write any of the two. Okay, let's write this first function, take derivative of second function, g dash x means derivative of second function, then we write second function as it is and take the derivative of first function. Okay, or you can take the derivative of first function first here and write the second function as it is. Okay, so it will not matter here. So I have written this function first and took the derivative of the first function, then I have written first function as it is and taken the derivative of second function. Very simple idea. Now we have here now logon, so the markers ink is getting diminished. Okay, so we have here 1 minus L raised power beta. We don't do anything with this, we take derivative of this function, so alpha becomes coefficient. Okay, we have WL alpha minus 1. Okay, then internally differentiate, so derivative of L is 1, so we are left with only W. So let me write it here, W. Okay, plus we have this WL raised power alpha and take derivative of this function by power function rule. Beta will become coefficient, we have 1 minus L beta exponent, which is beta, will be subtracted by 1 and then internally differentiate L here, so derivative of L is minus 1 and we set it equal to 0. That is how do we take the derivatives when we have two functions and they are multiplied to each other. Simple stuff. What I have done here, I have written 1 minus L to the power beta as it is. I have taken the derivative of this WL to the power alpha. Okay, if we have WL to the power alpha and if I want to take the derivative of this function with respect to L, so first this alpha will become the coefficient and this exponent, which is alpha, will be subtracted by 1. Okay, so first we use the power function rule and then we internally differentiate if any L is here. Okay, we have L here, so I have taken the derivative of L is 1 and I am left with W. That is how did I get this. And similarly we have WL plus alpha as it is. What is derivative of 1 minus L to the power beta? Simple, this exponent becomes coefficient. We have 1 minus L and exponent is subtracted by 1 and then we internally differentiate, so derivative of 1 is 0, derivative of L is 1, so this is minus 1 here. Okay, so simple explanation that I want to give you people. Now let's try to solve it again. So we have 1 minus L, okay, to the power beta. We have alpha here, I can write it like this, WL to the power alpha and WL. I have just expanded this, raised power minus 1, then we have W. Okay, plus we have here, let me do one thing here, I will transpose, since this is minus 1. Okay, so this whole term will become minus and I transpose it to the RHS, so this becomes plus. So we have WL. I have to do this here because I don't have the space. Alpha, then we have beta, 1 minus L raised power beta, okay, 1 minus L raised power minus 1, okay, is equal to 0. Simple thing, I have done nothing unusual here, okay. So I have expanded this WL to the power alpha minus 1, WL to the power alpha minus 1. It can be written as WL to the power alpha times WL to the power minus 1. And same thing I did here, okay. So empath kya karo? Let's find out. Let us see if we can cancel some stuff here. Let me use another, another color. The problem is the ink has diminished, rather the power of the ink to write has diminished. So 1 minus L to the power beta, 1 minus L to the power beta, they will get cancelled, okay, because these are terms are multiplied to each other here. Then we have WL to the power alpha, WL to the power alpha, they will get cancelled, okay. So we are left with alpha. Then we have WL raised power minus 1, and it can be written as 1 upon WL raised power plus 1 into W is equal to, here we have beta, okay. We just want to solve this function for L to see whether whether labor supply depends upon wage rate or not. Then we have beta, okay. So 1 minus L to the power minus 1, it can be written as 1 upon 1 minus L, okay. So W cancelled, we are left with alpha upon L is equal to beta upon 1 minus L. So doing cross multiplication, we have alpha 1 minus L is equal to beta L, okay, which implies taking B and this L here and this alpha here. So we have 1 minus L upon L is equal to beta upon alpha, okay. So I have transposed this here, it will get divided, and this alpha here, it will get divided. So this can be written as 1 upon L minus L upon L. I have expanded this term is equal to beta upon alpha. So we are left with 1 upon L minus 1 is equal to beta upon alpha, or 1 upon L is equal to beta upon alpha. Transposing this minus here, it will become plus, okay. Now where do I write the other step? So let me write it here, okay, because I don't have infinite number of space here, infinite space rather. So we have 1 upon L is equal to, so doing cross multiplication, it will become alpha plus beta upon alpha. So we have alpha plus beta upon alpha. Now reciprocating both sides, we have L is equal to alpha upon alpha plus beta. This is our labor supply, okay. Does this labor supply depend upon wage rate? We did not get here in this expression, there is no W. If there is no W, we can safely say that labor supply does not depend upon the wage rate, okay. So if for example, if wage rate was in denominator, okay, if we got this expression like this, okay, if we have wage rate here, then we could have said that labor supply is inversely proportional to the wage rate. By similar logic, if we got here W, okay, which we did not get, I am just saying here. Okay, if we got here W, then we could have said that labor supply is directly proportional to wage rate, but we did not get our labor supply in terms of wage rate, so we can say that labor supply does not depend upon the wage rate. So the first option is correct. Okay, I hope I make myself clear in this video. Thank you.